Welcome to this AP Precalculus lesson. Today, we're going to explore a specific feature found in the graphs of rational functions. Our main topic is holes, also known as removable discontinuities. By the end of this video, you will be able to determine the existence and location of these holes. Our learning objective is to determine holes in the graphs of rational functions. So, what exactly is a hole in the graph of a rational function? It's a single point that is missing from the graph. This happens when there is a common factor in both the numerator and the denominator that can be cancelled out. For a rational function r of x, a hole exists at a value x equals c if the factor x minus c appears in both the numerator and the denominator. Let's work through an example to see this in action. Consider the function r of x equals x squared minus 4 divided by x minus 2. Our function is r of x equals x squared minus 4 over x minus 2. The first step in finding holes is to factor the numerator and denominator completely. The denominator, x minus 2, is already factored. The numerator, x squared minus 4, is a difference of squares. It factors into x minus 2 times x plus 2. Now, we look for common factors. As you can see, both the numerator and the denominator have the factor, x minus 2. Let's highlight the common factor. Because this factor appears in both the numerator and denominator, it indicates that there is a hole in the graph at the value of x that makes this factor 0. In this case, that's x equals 2. So, we've determined there is a hole at x equals 2. We've achieved our first objective. Now that we know a hole exists at x equals 2, our next objective is to find its exact location, which means finding the y-coordinate. We need to find the point 2, L. We find the y-coordinate of the hole by using the simplified version of the function. Let's go back to our factored function. Since the factor x minus 2 cancels out, the simplified function is y equals x plus 2, but only for values of x that are not 2. Remember, the original function was undefined at x equals 2, and the simplified function must reflect that. The graph of the original function r of x looks exactly like the graph of the line y equals x plus 2 everywhere except at x equals 2, where there's a hole. To find the y-coordinate of that hole, we evaluate the simplified function at x equals 2. Plugging 2 into our simplified function, we get y equals 2 plus 2, which is 4. This value, 4, is the y-coordinate of our hole. It's the value the function is getting arbitrarily close to as x approaches 2 from either side. Therefore, the hole in the graph of r of x is located at the point 2, 4. Let's look at the graph to visualize this. Notice that the graph is the line y equals x plus 2, but there's an open circle at the point 2, 4 to indicate that this point is missing. This shows we have successfully determined the location of the hole. Now, let's look at another scenario involving multiplicity. Multiplicity refers to how many times a factor appears in an expression. A key rule to remember is this. If the multiplicity of a 0 in the numerator is greater than or equal to its multiplicity in the denominator, you have a hole. Let's repeat that. If the multiplicity in the numerator is greater than or equal to the multiplicity in the denominator, you get a hole. Let's apply this to the function r of x equals x minus 2 squared divided by x minus 2. Our function is r of x equals x minus 2 squared over x minus 2. First, we identify the common factor. It's clearly x minus 2. The common factor is x minus 2. Now, let's find the multiplicity of this factor in the numerator and the denominator. In the numerator, we have x minus 2 squared, which means the factor x minus 2 appears twice. So, the multiplicity in the numerator is 2. In the denominator, we have a single, x minus 2. Its multiplicity is 1. Now we compare them. The multiplicity in the numerator is 2, and the multiplicity in the denominator is 1. Since 2 is greater than or equal to 1, our rule tells us there's a hole at x equals 2. Because the numerator's multiplicity of 2 is greater than the denominator's multiplicity of 1, we have a hole at x equals 2. It's crucial to understand the difference between a hole and another type of discontinuity called a vertical asymptote. We've seen that a hole occurs when a factor cancels completely. So, if a factor cancels out entirely, the graph has a hole. A vertical asymptote, however, occurs when a factor does not cancel out and remains in the denominator. A vertical asymptote occurs if a factor remains in the denominator after you've simplified the function as much as possible. Let's modify our previous example to see this. Consider the function r of x equals x minus 2 divided by x minus 2 squared. Now our function is r of x equals x minus 2 over x minus 2 squared. Again, the common factor is x minus 2. Let's compare their multiplicities. In the numerator, the factor x minus 2 has a multiplicity of 1. In the denominator, it has a multiplicity of 2. This time, the multiplicity in the numerator is 1, and in the denominator it's 2. The numerator multiplicity is not greater than or equal to the denominator multiplicity, so there is no whole. Instead, when we simplify, one of the x minus 2 factors cancels, but 1 still remains in the denominator. The simplified function is y equals 1 over x minus 2. Because the factor x minus 2 is still in the denominator, there's a vertical asymptote at x equals 2. The key takeaway is to factor everything, simplify as much as possible, and then examine the remaining factors in the denominator to find any vertical asymptotes. Let's summarize. Wholes appear when a factor cancels completely. Vertical asymptotes appear when a factor remains in the denominator after simplification. By factoring and comparing multiplicities, you can easily tell them apart. Let's put it all together with one final example. Consider the function r of x equals x cubed minus 1 divided by x squared minus 1. Our function is r of x equals x cubed minus 1 over x squared minus 1. Remember, the first step is always to factor the numerator and denominator completely. The denominator, x squared minus 1, is a difference of squares and factors into x minus 1 times x plus 1. The numerator, x cubed minus 1, is a difference of cubes. The formula for difference of cubes is a cubed minus b cubed equals a minus b times a squared plus ab plus b squared. In our case, a is x and b is 1. So, x cubed minus 1 factors into x minus 1 times x squared plus x plus 1. Now we can write the factored form of our rational function. R of x equals x minus 1 times x squared plus x plus 1, all divided by x minus 1 times x plus 1. Let's identify the common factors. We see the factor, x minus 1, in both the numerator and the denominator. Its multiplicity is 1 in both. The common factor is x minus 1. Since its multiplicity in the numerator, 1, is equal to its multiplicity in the denominator, 1, it cancels completely. Because the factor, x minus 1, cancels completely, our rule tells us there's a whole at x equals 1. We've confirmed a whole exists at x equals 1. Now, let's find its location. Just like before, we need to find the y-coordinate of that whole. To do this, we use the simplified version of the function. After canceling the x minus 1 factors, the simplified function is y equals x squared plus x plus 1 over x plus 1. To find the y-coordinate of the whole, we substitute x equals 1 into this simplified function. Y equals 1 squared plus 1 plus 1 divided by 1 plus 1. This simplifies to 3 over 2. So, the whole in the graph of r of x is located at the point 1, 3/2. We have found the location of our whole. But let's not stop there. We also need to check for vertical asymptotes by looking at the simplified denominator. The simplified denominator is x plus 1. This factor did not cancel out. Since the factor, x plus 1, remains in the denominator, there will be a vertical asymptote where this factor equals 0. Setting x plus 1 equal to 0 gives us x equals negative 1. This means the graph has a vertical asymptote at x equals negative 1. Let's visualize the final graph. It will have a whole at 1, 3/2 and a vertical asymptote at x equals negative 1. Let's quickly recap what we've learned today about wholes in the graphs of rational functions. Wholes, or removable discontinuities, are single points missing from a graph. To find them, you must factor the numerator and the denominator completely. Then, look for any common factors. A whole exists at x equals c if the factor, x minus c, is common to both the numerator and denominator. The key rule for distinguishing between a whole and a vertical asymptote is to compare the multiplicities. If the multiplicity in the numerator is greater than or equal to the multiplicity in the denominator, you have a whole. If the factor remains in the denominator after simplification, you have a vertical asymptote. Finally, to find the y-coordinate of the whole, cancel the common factor to get a simplified function. Then, substitute the x value of the whole into that simplified function. Evaluate the simplified function at the x value of the hole to find the y-coordinate. You now have a solid strategy for identifying and locating holes in the graphs of rational functions. Great job today!